Thank for inviting me to this talk. First of all, I'm super excited to be able to give this talk here. I thank you also, the organizing, for making this possible to have so many presenters and orators to be here. So, okay, I will begin now. So I'm going to talk about some of my PhD thesis and studies that I'm doing right now with my advisor, Pablo Amster. So the title is On Persistence of the Nicholson Equation with Multiple Delays and Nonlinear Harvesting, as Elena was talking about just recently. So the idea of this talk is mainly show how using guiding function techniques and a reduction to a scalar case, we can show persistence and existence of periodic solutions. So let's begin. So first of all, let's give some definitions. So if we consider this delay differential equation, and where x prime is equal f, where f is defined in this domain, and of course is continuous. And we also consider this initial condition defined on this interval. Well, phi is from minus tau star to our n. We shall define a guiding function, a C1 function from 0 plus infinity n to 0 plus infinity, such that the inner product from between the gradient of b and f is greater than 0. In the literature, we can find here a different domain. We can also take Rn, and it's more common to have this inequality instead of norm of x, say greater than some constant delta. In our framework, we are going to use sets involving instead bx smaller than r, some R that I'm going to tell you about shortly. And we also were going to require that bx goes to 0 as x goes to 0. So the second definition we shall use for persistence will be that the solutions of the previous system and for the Nicholson equation will be that are strongly persistent if the limit of the norm of x is greater than 0 for all solutions, of course, different from 0. And similarly, the solutions are uniformly persistent if the limit of norm of x is greater than some epsilon sub 0, uniformly bounded for all solutions. So with these two definitions, finally, let's introduce this generalization n-dimensional of the Nicholson equation. So as you can see, I'm here having n equations, and I have displayed with all the complexity. We know that each coordinate is the population at time t, that d is the mortality rate, and tau sub g is the time to maturity, also known as delays. And in this setting, we're also considering this cooperations term, where we are considering the populations are being cooperative between each other, and then we are going to suppose or assume they are increasing functions. Lastly, not only have this explicit nonlinear function that is the most usual in the base of setting of the Nicholson equation, but we are also considering this nonlinear harvesting term that can and will be, let's say, joined with this term. We are going to consider the sum of the mortality rate and the harvesting term in order to analyze the equation. But for now, I just wanted to explain as complex x possible. Let's say that this is not linear at the beginning, and we're setting that this is 0. And as the times go, we can think that this can be linear and this have the non-linearity. But just to think as two different terms. Also, this is depending on each coordinate, and this is depending on all coordinates at the same time. So as before, the initial condition would be in each coordinate phi sub I, where phi sub I is now defined as a continuous function in this set, where now tau star is, of course, the maximum between all the delays in order to have well defined the equation. So that being said, let's start with some previous results. So one of the most important results are known from Berezanski, Braverman, and Idles that analyze the equation very extensively. I just going to mention some of them that it's inspired this work. If we have this scalar version, then we know that, of course, if P is smaller than D, there can be any equilibriums, and furthermore, 0 is a global attractor for any positive initial function. And conversely, if P is greater than the mortality rate, there will be an equilibrium. And moreover, what is interesting in this, just in our approach, is that the limit of the solutions are greater than these values that, of course, are positive. So this is just the first result that we have uniform persistence. In a more general setting, if we suppose that these functions are T-periodic, then we will have existence of T-periodic solutions if, again, P is greater than D for all T, and there are not going to be any periodic solution otherwise. And also, once again, 0 will be a global attractor. This also inspired the second results by Amster and Devoli, where we have now multiple delays and a harvesting term. So in this setting, we shall consider this function, which is uniformly in T, obviously, and continuous. And for the periodic case, they show that if this sum is smaller than the sum of the mortality and the harvesting over X, then the solutions tend to 0 and globally defined. And instead, if we have that this sum is greater than the mortality rate, and now from this limb sub, then there exists a periodic solution. Moreover, in our setting, this will show that solutions are strongly persistent. So with these results, we can finally set and show what have we done in this couple years, just say. So if we set G, the sum of D and H, the mortality and the harvesting, and set limit sub G over Y over X, and B sub 0, the limit of the cooperation terms over each coordinate, we shall obtain strong persistence if we have the sum of P sub J plus the cooperation terms greater than the sum of the mortality and the harvesting, again, having this limit. In some sense, we are saying that this is an extension from the linear case where we are having that this is bounded by each coordinate X. And we are going to obtain uniform persistence if we consider this inequality plus we bound this term by a certain set constant C sub 0. With these two conditions, we obtain uniform persistence. So let's see how this have anything to do with guiding functions. So the approach for these propositions, let's say, is consider this guiding function that is not smooth, but nevertheless it works. And the three cases to analyze a strong and uniform persistence are these three. The first one is just the one that it will show the strong persistence. That is, we want to, if we set R as the infimum limit of B sub t, we want to show that R must be non-zero or positive, of course, talking about populations. So in this case, the sketch to approach it is suppose that we have this sequence such that B of T sub n is the minimum in this compact set for B sub T. After that, we can pick a B subsequence, a coordinate, say, y sub 0, where B of T sub n is equal to this coordinate for all n. This allows effectively that we can go from the n-dimensional case to the scalar case. So, okay, this solves the first two because if we have this situation, then the derivative is going to be negative, and using these two steps, we are going to find a contradiction with this inequality in mind. But the problem usually are these two tricky cases where one of the main problems between others is that the solution and the delay solution, let's say, maybe the distance between of them may be large. So in order to solve it, if it's oscillating or is approaching from below, we will consider this key that says that the previous conditions allows to find this uniformly inequality, giving us that if we are approaching from below, then all the solutions are, then the derivative is always bounded by C, that giving a contradiction. And if we are in the other case, oscillating from above, then we can fix again another sequence and have this inequality and prove that via this subsequence we can reach to a contradiction. So, well, mostly let's say that using a guiding function, we go from the n-dimensional case to the scalar case, and thanks to the expected inequality, just say this, and this like standard uniformly bound, we can reach to our result. So next, let's say, is from persistence to periodicity. So the approach for this part of the talk will be use the condition that I previously mentioned and try to apply topological degree techniques in some appropriate region in Rm. So to do so, we will need lower and upper bounds. From the uniform persistence in the setting of T-periodic functions, we will get the lower bounds. Let's just say epsilon sub 0, as I stated in the first definition slide. And then let's choose these two functions. There are limit of G over xi and lim sub of bx over xl. And we are not considering the behavior as xi and xl approach to plus infinity. So the conditions we need to bound the dynamics of the population growth will be that this cooperation terms needs to be increasing, and we need to this inequality to happen for all t. Of course, I'm not explicitly showing that this is for all y and for all I and t, but basically we're saying that the mortality rate plus the harvesting is bounding the growth of the cooperation. So thanks to the three hypotheses, we get that exists a periodic positive solution. So the way to show it, again, just a sketch, will be to use the continuation method from Melanie and Krasnodębski that I guess that most of you or some of you know. So in order to do so, let's consider the interior of the positive cone of the C sub t solutions, C sub t functions, and then define omega as the functions that are between these two bounds. This is the bound that it comes from the uniform persistence, and this is the bound that comes from the upper persistence, no, let's say dissipativeness, but in any case are the bounds that we can get when we use these two hypotheses. So once we set omega, the idea is to consider an appropriate homotopy f lambda that I'm not going to explicit just because it's too technical, but the point is that f sub 1 is the Nicholson equation, and we are going to deal with f sub 0. In order to use this method, we have to prove that f sub lambda is non-zero at the boundary for all lambda between 0 and 1. After that, we can show the f sub 0 restricted to the constant functions in this space, sorry for that once again, is homotopic to a translation of the identity of Rn. In some sense, it's just applying the Poincaré-Miranda theorem, but translated. Instead of having this in a cube of minus 1, 1 in Rn, we are having that in this translated interval. So once we have these two conditions, is immediately that from degree invariance that the degree of F1 is different from 0 in the region, implying that we have a T-periodic positive solution. So basically we can obtain periodic solutions using uniform persistence and some kind of dissipativeness plus one condition more. So before finishing this talk, maybe I talked too quickly, but okay. Let's talk about two more things about guiding functions and persistence. So the first one will be to finish the analysis. Let's see that 0 is a global attractor if once again we change the sign of the inequality, and now instead of having this lim sub and lim inf functions, we can just have the inequalities with the sum and the definition of sheep. And if this is holds for all t, then all the solutions with the initial positive function tends to 0 as t goes to infinity. In order to prove this result, once again, the idea is to use a guiding function, but now we use, instead of mean, max, that is of course expected, and it's enough to show that u goes to 0 as t goes to infinity. So once again, the idea was to show that just choosing a guiding function, we can achieve to the result. So finally, I wanted to mention that during the analysis of this case, the Nicholson equation, is that in a previous work that we have already published with Pablo, we use another kind of a more general definition of persistence, and we also prove that we can have the previous results using different definitions. For instance, a more general way to analyze our problem would be just consider a semi-flow and say that a set of solutions or a system is strongly rho persistent if we have this inequality, and similarly uniformly rho persistence if we have this inequality. Now this function being not necessarily a metric, but in our case being a persistence of some species we have used the norm. We have proved that if we use some more abstract definition, the results also holds. For instance, if we have for each coordinate, or we use more Lyapunov type kind of functions, of course, with the gradient sign change. Well, that's all I wanted to tell you today. So I'm going to show you the reference from where we base the last results. Of course, there are so many more to mention. Since Therese is here, I wanted just to mention that also I have been like reading most of her works about relating Nicholson equation. And well, thank you so much for your attention.